I'm Chase Romano. I'm joined by Caleb Bechtold here. We're principal AI/ML architects at Snowflake. And today we're going to talk to you about best practices for cost-effective machine learning. And the agenda today is going to be about a couple of different personas here. So originally, where does ML cost come from in Snowflake? And we're going to go over this from a data scientist point of view, maximizing that while you're developing, while you're putting it in production. The ML engineers, when you're orchestrating the price performant continuous inference. And then for the platform owners, like as an organization, how are you going to get the best cost performance in Snowflake when it comes to machine learning? All right, so where does ML costs come from in Snowflake? First, you've got your compute inefficiencies from legacy platforms. You're migrating something over. You may not have the correct infrastructure set up. And then when you move it on over Snowflake, which could be a little bit of a different scenario for you, actually setting up that initial compute infrastructure can cause some headaches when it comes to price performance. You'll see in our marketing, a lot of the times we say, oh, Snowflake was 70% cheaper during this migration for ML. A lot of that sometimes will come from the data movement that no longer needs to happen. You can now perform your machine learning training and your inference directly in Snowflake without having to move data out of the platform. And then on top of that, you now have a faster time to value. So think about the people, the resources, the time that it takes to actually take a machine learning model from development into production. It's going to save you a lot of money. So I'll hand it off to Caleb for our next topic.
So part of the challenge here, as we think about those three kind of primary cost dimensions, if you look at what a typical legacy kind of machine learning platform looks like, especially for customers, which we see very often who use Snowflake already today as a primary data source and potentially a data sink for machine learning models. The differences between kind of what the legacy setup looks like and how this works in Snowflake are direct contributors to where a lot of the cost comes from with doing ML. You have, of course, like Chase mentioned, data movement, which incurs query costs, time costs, additional compute costs for a separate platform to now process that same data in a different way, along with write-back costs into the Snowflake environment. You have cost complexity with managing a multitude of potentially disparate services that serve specific kind of components of the ML lifecycle, and you have engineering overhead that comes with managing and orchestrating how all these different systems talk together and how you ultimately deliver production machine learning insights back to the business. On the Snowflake side, we've aimed to streamline that process, simplify it dramatically, and ensure that the compute surface area that you're working with on the Snowflake side is optimized to give you maximum efficiency and maximum price performance over an alternative. There's a whole host of ML capabilities in Snowflake, some new, some have been around for some time. We'll have at the end of this session kind of a link to all the various deep dives and breakouts that'll go really in depth over a lot of these different components. I especially encourage you to check out the What's New ML session a little bit later on to kind of get into like the nuts and bolts of how to use these things in the best way. And we're going to look at them each kind of from a cost standpoint in this session today. The first thing I'll call out, though, is fundamentally in Snowflake, you pay for compute. You pay to process data. Your SQL workloads, you do this on the virtual warehouse today. When we talk about cost in ML, it's the same concept. You pay for compute to process data and to train machine learning models. So we're going to focus a lot on how to get the most out of that compute through these series of best practices. Let's start with the data scientists, folks who are actually building the models and how you can build machine learning models at scale in Snowflake. So the best practice number one, use the container runtime for machine learning development in Snowflake. Container runtime runs over top of Snowpark Container Services compute, which are offered from at just a unit economic level, extremely kind of competitive, per hour pricing on the instance types. But the container runtime comes with a lot of internal optimizations to scale machine learning effectively. It's a pre-built service that runs over top of an open source Ray cluster in the background, giving you super efficient distributed machine learning training operations, and coupled with a whole bunch of additional capabilities like our DataConnectors, parallelized hyperparameter tuning, Bayesian optimization for machine learning workloads, and much, much more on top of CPU and GPU access. So if you're building ML, use the container runtime first. You're going to get maximum performance at better unit economics than you would with alternative solutions.
Now, let me ask you a question real quick. In the room, I hope we have some data scientists in here, especially if you're at the session. How many people, I know you hate doing this, but don't be shy. How many people have used our warehouse runtime notebooks? Like, raise your hand. They've been out for a very long time. Keep them up. Keep them up. If you've used our warehouse runtime notebooks. Now, I want you to keep your hand up. I want you to put it down if if you've actually used our container runtime as well. Okay, that's really good. People who still have your hand up, listen to what he said. Switch to container runtime, right? It's going to be one of the things that's going to help you save costs immediately. And those of you that didn't put your hand up at all, if you don't know, go use our container runtime notebooks. It's really going to help with development. And again, you're going to get really good cost performance out of it.
The number 2 best practice is scale your feature development for both model development and model inference using Feature Store and support better reusability and cost efficiency. A lot of times when we talk to customers about Feature Store, the most common conversation is not why use Snowflake's Feature Store, it's why use a Feature Store, period. Until ML teams reach a certain scale, a lot of times they don't realize what Feature Store gives them from a governance, reusability, and cost efficiency side of things. One of the biggest things that a Feature Store gives you is eliminating duplicate processing of the same data for the same features to support potentially multiple workloads or multiple use cases. When you define features in a reusable version, shareable way, you process data incrementally, first and foremost, to get updated feature calculations, which is much less compute than doing full refreshes or full feature computations every time you need to run a training or an inference job. But you also eliminate the risk of one data scientist calculating the 30-day average order purchase amount for each customer, and another data scientist calculating the exact same feature over the exact same data to support both your propensity modeling and your customer churn predictions. Why process the data twice when you can process it once incrementally in a fully reusable way and minimize all this duplicate compute that you might be spending already today just to build out pre-processed data to go into your machine learning models? Importantly, this Feature Store does use the best of virtual warehouse compute in Snowflake as well. When we're talking about feature development, we're talking really data frame style processing, scalable kind of MPP type workloads, which the virtual warehouse is really good at doing efficiently. And when we do that incrementally using Snowflake Feature Store, we're also minimizing the amount of data reprocessing and duplicate processing that might otherwise typically occur in an ML workload. Number 3, using that container runtime, scale your training compute on demand. Snowpark Container Services as the backend compute layer to the container runtime allows you to specify different cluster sizes and configurations with min-max node counts and all these sorts of things. But importantly, not every step of an ML development pipeline needs big, beefy resources. And so the container runtime abstraction gives you really simple ways and simple APIs to scale up compute on demand at the point that you need it in your model training workflow, to run a large-scale GPU model training job, or to distribute some sort of hyperparameter tuning and optimization task, maximize the underlying VM utilization in the background, but also do this dynamically. So you use right-sized compute for right-sized jobs, and also don't waste money on compute that you're not using when you don't need it. This can happen mid-execution, whether we're talking about kind of an orchestrated production workflow or an interactive development workflow in a notebook environment to get more compute accessible to you just at the point that you need it, and then quickly bring things back down once the training jobs are complete. The last one on the development side is also use the data connectors. Data connectors in the container runtime are super efficient at bringing large-scale data sets into the container runtime for those distributed training and distributed hyperparameter tuning tasks along the way. These are immutable data set objects that allow you to bring that in without incurring significant select query costs. Parallel loads the data into it for large-scale development tasks, has native support for things like PyTorch datasets and TensorFlow objects, and allows you to also scale this limitlessly across your compute resources without wasting a bunch of compute just getting access to data for your model training jobs. So use the data connector APIs as much as possible for those training jobs.
All right, and next for ML engineers, optimizing production pipelines. So we're going to get into model serving and inference. Once you've done your training, Caleb's talked about our feature store, model development. What is model serving? So at the core of it is our model registry. And you can log your model, and you can choose to deploy this on either a warehouse or Snowpark Container Services, and they both fit different situations for what you're going to want to use. Now, when you use the warehouse, you can get inference via the SQL query right away, and you can get that as well with the Snowpark Container Service, but I'll talk in a little bit about batch versus near real time. So why do you want to use this? I don't know if anyone's ever created a model in Snowflake, or even you've brought one externally into Snowflake, and you have to create a Python user-defined function, and it's a lot of extra code, you've got to maintain it. With the log model and the model registry, we create the user-defined function for you. Okay, so it's created in the back end. You can call it via SQL. You can call it via Python, and we manage all of that for you. You'll get distributed inference on the CPU or GPU, and you can now use this with any pip package. No longer bound by the Anaconda channel. I know that was a big problem for a lot of you a while back. No longer bound by that. Again, distributed inference, and you're able to log all of this and have it create the UDF for you. Now, after you've done that, you want to deploy it in the right way. So if you have a very large scale batch inference use case, warehouses are going to be a great fit for this. You can do CPU inference at scale. They're great for large inference jobs, and it integrates with Python or SQL, and it's very low barrier to entry. So super easy to set up once you've logged your model in the model registry. And then when it comes to online and GPU inference, that's when you're going to want to use your Snowpark container services. So again, you can get CPU and GPU inference in near real time. You can get second latency, right? Infer using any custom model you want via SPCS. You can have ingress endpoints enabled for external access, and it's great for customer-facing interactions such as an external website. And then you also have the many model approach, right? Training multiple models in parallel using partition modeling on the warehouse or container runtime. Seeing a lot of customers using this for time series. It's a very, very common use case for distributed training, right? When you're wanting to do this many model distributed training. And then again, you can perform large inference on many, many partitions doing it this way. And then when we get into inferring incrementally, how you're going to schedule this, how you're going to maintain this. First one we'll talk about is task-based. We've had task for a while in Snowflake. We now have the ability to do this via custom DAGs via the Python API. Easily chain these jobs together. You can set your cron schedule, and then you get more flexibility and control with that. Now, if you want to do batch, but you also want to just set a lag, you don't want to set it at an exact time. Maybe you got some tables that that have data getting ingested into them, and then you want it to do the inference once there's new data in those tables at a specific lag. Dynamic tables are a great fit for that. So it abstracts away that whole stream and task process. You don't need to do a task based on a stream. The dynamic table handles all of that for you. You literally just set the lag, the warehouse, and give it the query. And as the tables downstream, once they've got data in them, we will now perform the inference incrementally for you. And then individual and online, this is where you can serve near real-time inference via that external endpoint. And then with that, all the cost on this is on the compute, right? And with container services, you can get really small compute or you can scale very large. So you've got way more flexibility on the container runtime side.
And it's just like we said with Feature Store, right?
Yeah.
Fully refreshing data to perform production inference is expensive, and incremental inference is not. So the constructs in Snowflake to support incremental jobs through dynamic tables, through streams and tasks, can give you really, really predictable cost, importantly, but also really efficient and manageable cost and control, just like you deal with today, maybe for typical data transformation pipelines as well. All right, let's think about then how do we do this at scale? So we talked a little bit about how developers and ML engineers can get the most out of the compute for their ML jobs. What does it look like now when I have teams of hundreds of data scientists and lots of different users and lots of different use cases that we're thinking about deploying into our Snowflake environment? One of the things that ML in Snowflake is really good at is providing really simple and seamless environment level separation, as well as granular cost control mechanisms over different compute resources through role-based access control. I am not a database and or security guy, and so I usually hear role-based access control and my eyes start rolling to the back of my head and all these sorts of things. But when we're talking about managing a whole platform for a large set of data science users, role-based access control is fundamentally your mechanism for how you both manage access, but also manage cost associated with ML. And so what we see a lot of times is that customers and customers who do this successfully set up some notion of environment level separation in their Snowflake account. And you can do this a couple of different ways through both database level separation or account level separation, where you have sort of dev, stage, test, prod accounts or databases. And that should extend to your ML users as well. The reason for this is that ML objects in Snowflake, be they feature views, model objects, whatever it might be, are fundamentally schema level objects themselves. So when you separate out dev and prod, you can give your data science users very elevated privileges into that dev environment so that they can experiment, create objects that they need, kind of, live in a bit of the wild, wild west without risking, affecting any sort of production pipeline. They can create features as they need. They can iterate quickly. They can run hyperparameter tuning jobs and experiments and evaluate those and all these sorts of things without a lot of restriction. But you can also do it in a way where the roles that allow them access to this dev world also have very specific compute pools and virtual warehouses that you can put tighter cost controls around for development specifically. A lot of times these are going to be shared compute pools that can scale a bit more dynamically maybe, so that you have lots of different data science users accessing it and working in the shared compute environment for these dev workloads, but not blowing out the budget necessarily by just spinning up huge amounts of compute or whatever it might be. The flip side of that then is in prod, because it doesn't cost anything to have compute in Snowflake, it just costs you to use it. You can also, the same practices we preach around isolated virtual warehouses for different workloads for kind of SQL type workloads, extends to the compute pools for your production training jobs as well. You can have dedicated compute pools that are right sized and right configured for the task at hand in prod, that only your service roles and service users and CD pipelines are actually able to touch and interact with, and have different budgeting, resource monitors, things like that over top of your prod environment that gives, again, very tight control, visibility, and easy management of where that production cost comes from, that's completely isolated from what data scientists might be doing over in the dev world and is managed slightly differently. So that dev and prod separation gives you this flexible permissioning, gives you dedicated compute to both isolate workloads, but also manage the cost of those different compute resources, and really granular cost visibility. If you're trying to figure out how much am I spending on data science development today? Well, if you have dedicated compute resources that are for those data science developer roles and personas today, there's a ton of data in the information schema views and the cost monitoring dashboards and all these sorts of things that allow you to see exactly what I'm spending for data science development. And similarly for your production pipelines, how much is it costing me to host my customer churn model in Snowflake today? If you have dedicated compute where those production workloads are incrementally running through whatever orchestration mechanism you're using, you can see all of that super clearly in all the FinOps tooling that exists on Snowflake today. The last one too, budget, monitor, and set up alerts. Again, as a data scientist, I usually say somebody else's problem, but as a Snowflake platform owner who's enabling your data science and your ML teams, it's important to have these controls in place. Things can explode, get out of hand if you just let people go wild without some kind of controls and visibility in place. And so utilize those same kinds of capabilities for your ML teams and use environment separation as a way to really granularly see exactly and allocate and be able to tell where the cost is coming from fundamentally, and set up your alerting and different actions you might take when those costs start to reach maybe some thresholds that you've agreed upon and are configuring. We talked about some 8 different best practices here throughout the life cycle. Hopefully the takeaway is that optimizing Snowflake ML cost is simple. It means different things depending on who you are in your organization and how you work with ML on Snowflake. But use Snowflake for cost-efficient ML. Set up compute, use that compute, pay for that compute. Don't worry about licensing fees or anything else like that. Because we charge compute-based spending for ML fundamentally, just check out the pricing sheet. Get a feel for what Snowpark Container Services in particular and the different instance type look like from a cost model. And you should be very familiar with those. It's really the billing model is the exact same as the virtual warehouse. You have compute, you pay for it. So take a look at that. Thank you all so much.
Thank you.